So I'm going to do one more problem like this. It's got two sources, so we might argue we could use mesh analysis and we come up with three equations, or node analysis. You do it with one equation with node analysis, so maybe node analysis would be the preferred way. But I think I want to try superposition on this, which means that we're going to look at one source at a time. We'll look at what the contributions to the voltage source is for this voltage V of t here, because that's what we're looking for in this thing. That's the unknown right there. And then we'll look at the contributions of the current source. I think this is a problem out of your textbook or a past edition of your textbook, but fairly typical problem. We'll note no initial energy storage, so the capacitor doesn't have an initial charge, the inductor doesn't have an initial current, so that would keep things a little bit easier. But as we think about superposition, usually with superposition, if it had dependent sources, we avoided superposition and would go to node or mesh analysis. Since this doesn't have dependent sources, superposition is probably a good candidate for that. And the tools that we will use, or maybe not tools, but the process is to short the voltage sources and solve it. And then we're going to come back and open the current sources and solve it. And then we'll add those two solutions together to get the entire problem. So our problem will break out something like this. If I look at shorting out the voltage source, I'll have a problem that looks like this. So we got the current source left. This capacitor that's 50 millifarads. It's not micro, milli 10 to the minus 3. And then 1 1/4. So let's see, 1 1/4 henries would be what, 5/4 henries, and 2 ohms there. So I'm going to call this voltage up here. I'm going to take this as the reference voltage, ground. And I'm going to say that this is V1 of t. And then when I do the other part of the problem, I'll have V2 of t, and I'll add those together. I'm not sure that I would recommend using superposition on this. I think as a learning process, it's good. But I'm going to use node analysis on this. If I'm going to use node analysis to figure out my superposition, I'd probably be better off just going and doing node analysis on the original circuit. But anyway, we'll get a little extra practice with this and be okay. Yes? On the current source, that's just U of t. This is the step function. So same thing over here on the voltage source, 20 U of t. So I'd presume it would be 5 amps and 20 volts, and then the U of t indicating we're turning those on or have some sort of a switching mechanism there. So if I look at the currents here, I can talk about this current going through here and that current going through here, and then I need to deal with the current here, and of course we are left with this current there. So I could talk about the current through here, through this 2 ohm resistor, is as simple as saying V1 of t divided by 2, right? And then I'm going to add to the current through the inductor. That's what 1 over L times the integral of V1 of t dt plus I at t naught, which no initial energy, so that's 0. Plus, and then what's the current through a capacitor? That's C times the derivative of the voltage, d V1 of t dt. So we've got that current, and that current. They're all leaving the node. This current is entering the node, so I'll just put this on the other side of the equal sign and say that I have 5 U of t. So I'll make some substitutions here. I've got V1 of t over 2 plus, if I look at L, which is 5/4, this turns out to be 4/5 when you invert it, times the integral of V1 of t dt. This term goes away because we had no initial energy storage. And then I have 50 times 10 to the minus 3, because that's milli, not micro. A pretty good sized capacitor. d v1 of t dt is equal to 5 u of t. So I guess it's time to go now into the S domain. So I have, what, 1/2 v in the S domain plus 4/5. This is the real bargain here with integration. So I'll have v in the S domain over S plus then what, 50 times 10 to the minus 3. I'll have that constant times S v in the S domain minus v naught, or v at t naught, let's say, which is 0, is equal to what, 5 over S. And I should probably call this v1 in the S domain because we'll eventually have v2 in the S domain, but I think we can keep it straight. I think we'll be okay. So grouping up the terms then, coming up here and borrowing some space, I think that I would have v in the S domain factoring out, what are we going to have? 1/2 and then 4/5 or 4 over 5s, so plus 4 over 5s plus 50 times 10 to the minus 3. Anything else? No. That's equal to 5 over S. So I could say then, solving for v in the S domain, that I have 5 over S divided by 1/2 plus 4 over 5s plus 50 times 10 to the minus 3. And you've been down this road many times. Yes?
When you multiply the value of the capacitor through that, you forgot the S.
Did I forget the S? Oh yeah, I better have the yeah, that should be over here. You're saying I forgot an S there. Right, you are. And that should be an S. We good now? Okay, great. Okay, thank you. So I think what I'll do is multiply by what do I do? Multiply by S and maybe 20s. Is that going to work for us? Yeah. So I'll take 20s and 20s. So when I do that, what do I come up with? 100 divided by 10s plus what, 16 plus, let's see, 50 times 10 to the minus 3 times 20 gives me, that's 1, isn't it? Yeah. So S squared. Okay, good. So I could factor this thing, and I could write this piece here as S squared plus 10s plus 16. Most people recognize that. When you factor it, what are our terms going to be? S plus 2 and S plus 8. Does that get us? Yeah, that gets us what we want. So we have then that v in the S domain is equal to 100 divided by S plus 2 times S plus 8. It's just sitting there ready for partial fractions, right? So let's go do that. So we had 100 divided by S plus 2, S plus 8 is equal to A, or K1, divided by S plus 2 plus B or K2 divided by S plus 8. So in solving that, I would say that A would be equal to what? 100 divided by S plus 8 evaluated at S equals minus 2. Yeah. So A turns out to be equal to 50 over 3. And B, likewise, would be equal to what? 100 divided by S plus 2, evaluated at S equals minus 8. So B turns out to be equal to then minus 50 over 3. So to complete this process, we have 50 over 3 divided by S plus 2 plus a minus 50 over 3 divided by S plus 8. So I could put it back into the time domain, V1 in the time domain, and this is just for the first part of this, is going to be equal to 50 over 3e to the minus 2t plus a minus 50 over 3e to the minus 8t, and that will then be u of t. So this would be due to the current source. Isn't that? Yeah, that was the problem. That's due to the current source. And that's probably one value of doing this with superposition. If you wanted to figure out the contribution from each source, again, if you really just wanted this voltage, it'd probably be easier just to take this as your reference, take that voltage as your unknown, and write your single node equation. But anyway, we'll check this, continue to check this out. So that's just due to the current source. Let's look at what this looks like if we want to look at the voltage source. So I come back to the given problem, and we said, what do we do with voltage sources? I've done the current source, so I want to put the voltage source back in. So I'm going to draw something with the voltage source. There's 20 u of t, and the resistance, the inductor, we'd have the capacitor, and what did we say we were going to do to voltage sources? Let's see. Open the current sources. So I need to open that current source, so I'm going to have something that looks like that. That will be opened up. Okay. I put the values in there. This is still, 5/4 of a Henry. This is 50 millifarads. We've got 2 ohms. Take this as my reference here, and I better call this V2 of t. So I can write my mesh equations. What are those going to look like? Well, if I want to find the current going through here, if I want to find that current there, I've got to find this voltage here, don't I? So I'd have to subtract off 20 u of t plus V2 of t and divide that all by 2. So that's that current right there. And then when I look at this current here, very similar to the last part of the problem that we did, we'll just have 1 over L times the integral of this time V2 of t dt plus I T naught, which is 0, no initial energy stored. So I've taken care of that current. And then lastly, what do I have? I've got this current through here, which is going to be what? C dV2 of t dt. So I've taken care of the current through the capacitor. That's all that we have, so Kirchhoff says that's equal to 0. So let me change things up a little bit, clean this up. V2 of t divided by 2 plus if L is 5/4 and we invert that, we get again 4/5 integral v2 of t dt. That term is 0 plus c, which is 50 times 10 to the minus 3 dv2 of t dt is equal to, now I left off this minus 20 u of t over 2, and move it to the other side, it becomes positive, so we will have 10 u of t. So I think I'm ready for the Laplace transform, right? I'm going to have what? V, maybe I should say this is V2 of S. We didn't say the other one was V1, probably should have, but I'll distinguish this. I'll say it's V2 in the S domain over 2, plus what am I going to have here? V2 in the S domain divided by what I'll have 4/5, and I have then S, and then what do I have? Plus 50 times 10 to the minus 3, and we have V2 in the S domain times S minus, is that minus? I think that's minus when we do that. V2 T naught, which is 0, is equal to 10 over S, right? So I could say, factoring out a V2 in the S domain, I have a half plus 4 over 5S plus 50 times 10 to the minus 3, and this time I won't forget the S, is equal to 10 over S. And that looks, does that look like what we had before? Fairly similar. Everything's the same except for this term right there, right? Okay. So it's the same except the numerator is twice as large, right? Okay. So do you want to go through the partial fractions, or do you want to just go to the solution? Because if we know the numerator is just twice as large, the solution should be pretty easy, right? Yeah, twice as large. I can just take this solution here, and we can say that therefore I have V2 in the S domain is equal to 50 over 3 would be twice that. I'd have 100 over 3 S plus 2 plus a minus 100 over 3 S plus 8, right? Everyone's okay with that? So I multiplied the numerator by 2. I'll finish this up then. So I need to take the Laplace or inverse Laplace transform of that. So if I look at this V2 of t, that's going to be equal to what? 100 over 3 e to the minus 2t minus 100 over 3 e to the minus 8t u of t, and this is due to the voltage source. So if you want to know the contribution in the individual sources, this would be a good way to do it, although probably the most direct way is just to do one node problem. Node or mesh are pretty powerful. Well, let's take the solution of this one here, and I'm going to add these two together, right? So I could say, get this up. Yeah, because if I'm looking for, if I'm looking for this voltage right here, across there, I'm going to add the two voltages together, the contribution of the current source and the contribution of the voltage source. So let me add those up. That is adding, get these all on here. I've got this one that I'm going to add to that. That is to say that V of t is equal to V1 of t plus V2 of t. So what's that turn out to be? We have 50 over 3 plus 100 over 3 gives me what? 50? 50 e to the minus 2t. Then those are both negative, so I'd have a minus 50 e to the minus 8t u of t. Okay. That would be the final answer.
Is the voltage across the inductor just the sum of those two because you have the sources on either side?
Well, what I had, and it would have been nice to have these on the same page here, is I said that, got a lot of stuff here. So here was our given problem right here, right? And I said that that was equal to essentially this one and this circuit superimposed on each other. So I solved this one for the voltage across there, and I solved this one for the voltage across there, and when I superimposed those on each other with superposition, I added the voltages together, and that got me the voltage across that inductor or the voltage across the capacitor, either one.
So you said this was difficult with other.
I think it's probably a little longer than just doing node analysis, because I mean, if we just wanted to do node analysis, we'd come up and write the node equation. You got a node current there, a current there, a current here, which we essentially had to figure out in any one of those, right? And then we would have just had to include this piece here. So we could have probably done it quicker in one fell swoop. But that gives you something to practice on. You can sit down and see if you can do it with node analysis, and what answer should you get. You better come up with this, right? Well, that was the last problem that I wanted to do, so I guess that gets us to a pretty good stopping point. Let me make sure you all know that this is... What's that? The node analysis. If you're going to do node analysis, do you want to go through the node analysis? So, if you're going to do node analysis on it, it's just node analysis. You got so let's see, we've got 2 ohms here and 5 force henries and 50 millifarads. So I would just say, I mean, if we're looking at this voltage, I would just call this V of t. I mean, you can call it V1 or V2. It's not going to be the same V1 or V2. I mean, it's the sum of those V of t. Take this as your reference here. And when you go to write your node equation, you're going to look at this one here. So you're going to have to find that voltage, right? So you have minus 20 u of t plus v of t divided by 2. Then you're going to have, what do we have for the current through our inductor? 1 over L times the integral of v of t dt plus I at T naught, which is of course 0 because we've got no initial energy storage. Plus then we've got to do the current through the capacitor, which is C dV of T dt. So that's that. And then what are we left with? We've got this one, we've got that one, we've got that one. We're just left with this, aren't we? So we'd have a minus, because it's entering at 5 u of t is equal to 0. So it's just a matter of solving that. And we've seen all those terms before, because it's effectively the sum of the two problems that we did, right? So questions with that? That'd be a good review problem. Take that and see what answer should you get. You had better get to this answer right there. It'll be the same final answer for V of t. Questions with that? Well, that gets us to a pretty good stopping point. So stay at the end. Okay, so